All right, let's learn about thermal inversions. They're certainly something that people like us who live in metropolitan areas need to concern ourselves with because it turns out when most of the um, health consequences of pollutions, other than like long-term ones, but the acute conditions happen usually during these weather phenomena known as temperature inversions or thermal inversions. So let's just see how they work. So remember, ordinarily in the troposphere, between the ground and 10 kilometers up, we have a general decrease in temperature with altitude. We call this adiabatic cooling. So if I was to attach a temperature sensor to a weather balloon and let it go at ground level when the temperature say 21 degrees, we find that if it goes up 1 kilometer, generally speaking, in most parts of the world, there'll be about a 7 degree drop for every 1,000 meters. So now it'll be 14 degrees. It goes up another kilometer and now it's 7 degrees. It goes up another kilometer, now it's zero. It goes up another kilometer, now it's -7. It will continue all the way up until it gets to the tropopause, which is about 10 kilometers up. That's called adiabatic cooling. Now, what's important is that in an urban area, pollutants that build up can normally dissipate away just through the normal actions of diffusion. If you recall that from chemistry or from biology, anytime you have a high concentration of particles, just by virtue of entropy, they will tend to dissipate from areas of high concentration to areas of low concentration unless they're confined, like say in a beaker. And so under normal conditions, there's no constraints. So it just diffuses outwards. And that's good for us who live in urban areas because although we're generating a lot of pollutants, they dissipate away from us and we don't suffer catastrophic health conditions as a consequence. So we aren't poisoned by them. But that changes during a thermal inversion. So what happens in a thermal inversion is we get a layer of warm air over a layer of cold air. So instead of it being warm as here and cold as here, we get this layer in between that's warm. Okay, and when that happens, it's called a thermal inversion. It's sort of not normal. And what happens is it act like a cap. It acts like a constraint, so that you can't let go of pollution, and then the levels of pollutants can get quite high. So let's just see how these things would go about forming. Okay, so remember, under normal conditions, we're going to allow the dissipation through diffusion of all these pollutants, and although we're generating, they're moving away from us. But but when there's an air inversion, it can't move upwards because the cold air is trapped by the warm air. Because remember, uh, warm air is less dense than colder, so it floats on top of it. So this air won't let this air up into it, and it's like being in a sealed jar now. So just as diffusion of say a dye in a beaker can't go out forever, that's the same thing that happens here. And so as we put more and more smog into the air, it can't dissipate, and it can get to lethal levels. Okay, so let's just say there's three different ways that it forms. There's what are known as radiation inversions or radiative inversions. There's subsidence inversions, which means lowering air, and then there's frontal inversion that has to do with the weather front. We'll look at each of these in turn. Let's just start off with a radiation inversion. So the kind of radiation we're talking about here is infrared radiation. Remember, at all times, day and night, the Earth is going to emit infrared radiation because it has atoms in the surface are moving, and moving atoms always give off radiation. Now, on average, the surface of the Earth is say 15 degrees, so 15-degree atoms are going to give off radiation. 0 degrees, -10 degrees, it doesn't matter. If as long as you're not at absolute zero, you're giving off radiation. Well, what that means, we're carrying energy into space. And so as long as there's no clouds to catch that infrared light and re-radiate back to the ground, then what happens is it can get colder and colder and colder at the ground, and that cools the air immediately above it. And we can get this pool of cold air that's maybe, say, half a kilometer deep. Now, I say clouds will stop it from happening because they'll re-radiate it back down and keep it from getting too cold down at the ground level. The other thing is if we have turbulent, if windy conditions, even though it can still get cold, there's a lot of mixing that happens. So we don't get this, we don't establish this pool of cold air that then is capped by warm air. But when it happens, it can be quite bad. So here's what happens. Here's our cooling curve, right? Adiabatic cooling in the afternoon, let's say 3 in the afternoon, 15 degrees at the surface, and we just go 10, 5, 0, -5, so on, all the way up. It's a typical adiabatic cooling curve that we'd expect anywhere on the Earth. But now what happens is the sun goes down and the world radiates away its infrared light, and then the surface of the ground gets cold. Well, the air that's touching the surface of the ground is going to get cold because of conduction. And then as the ground gets colder and colder, more energy is going to flow out of the air and into the ground because remember, heat always flows from where it's warm to where it's cold. So the air near the ground, say up to maybe 500 meters, is sending energy into the ground trying to warm it up. And so I get a curve that looks like this instead. So by sunrise, instead of having this, I have this. This region here is where pollution is going to build up. So my inversion is essentially happening in this region here, and this region here is the cold air below it. And so when the morning commute occurs, and we start putting pollutants in the atmosphere, they tend to build up here. And you can literally see these if you just pay attention. In the next few weeks, you can see it happening. It happens often enough, especially in the season we're moving into, in the winter season. You'll just see this layer of pollution. That's not necessarily. You might think like, well, that's just how high up the pollution goes. No, that's the boundary between the warm air up above and the cold air below. When you see this distinct layer where the smog stops, you're usually looking at a thermal inversion. Now, this is, and let's just talk about. There's a number of ways they can form, but let's just talk about radiation inversions. Okay, so the good news is they tend to burn off by early late, say late morning, early afternoon. Here's why. Okay, so again, in the afternoon we have this. As it gets colder and colder, and as the ground gets colder and radiates away its energy, the air near it cools down because of conduction, and we end up getting this layer of cold air. So when the sun comes up, we have this uh, layer of cold air with warmer air above it. So we have a thermal inversion, and the pollution can build up and build up during the morning commute. And by 11, the ground is starting to get warmer, and by noon to 1 o'clock or so, we go back to having the same kind of cooling curve. And at that point, then all the pollution can dissipate and we can all breathe easy again. But for a number of hours in the morning, it can be quite bad. And people can get hospitalized. The air can get quite toxic during a situation like this. Now, it's also worth noting that uh, there's because it's cold, there's often water droplets in the air, fog, and so sometimes this happens. You think, well, is this pollution? Is this fog? And the answer is it's usually both. So, if it's cold outside, we're talking like almost down close to freezing cold. The air looks bad and it's foggy. It's probably a radiation inversion. Now, radiation inversions are far more common in the winter months and spring months. So in the coming months, we're going to see these here in the greater Seoul metropolitan area. And it's because the ground is already cold. And so it's cooled down, maybe a meter or more into the ground has been cooled down. And so when the sun sets low in the sky, man, it's easy for the ground to get very cold and cool the air next to it. So we typically find is these radiation inversions are more of a winter spring phenomena than they are a summer fall phenomena when the ground is already warmer. Now, another way we can get inversions is what's known as a subsidence inversion. That means we have air subsiding or coming down from above. Now remember, as air goes up and it expands, the temperature goes down. But if you do the opposite, if you compress air, it heats up. Now, a couple examples, like if you go scuba diving, you take your scuba tank in when it's empty to a scuba shop, they hook it up and they start pumping air into it. That tank gets really hot. They have to put it in a water bath to bleed away the heat. Another way is to think about this is in a diesel engine. So in a normal car engine, as you compress the fuel air mix, you have to have a spark plug, like put a spark in there to cause the explosion of the fuel air mix, but not with a diesel engine. Diesel has a lower flash point. So what happens is it's just the compressive heating alone is enough to trigger the reaction. So if you take that cylinder of diesel and air and you compress it, the temperature is going to go up hot enough to trigger. My point is, when you compress air, it gets hot. So as air comes down, as it subsides, it's going to be compressed. And as it's compressed, it's going to warm up. And then what happens is, if it's warmer than the air below it, it won't sink any lower because of density. Warm air is less dense than cold air. So now I have cold air below and warm air above. Where below, I cooled this air down and left this at its ambient temperature. This is the opposite. This is at its ambient temperature, and this one got warmed up. Now, these are worse because they can be quite pervasive. Whereas a radiation inversion might only last until noon or 1, these things last sometimes for weeks. Okay. Now, there's a couple conditions that lead to them. Let's look at this one here. So, like Los Angeles is a classic example. You have air that's coming out of the east. It's being compressed as it's pushed up against the Sierra Mountains. It goes over and then it comes down. As it comes down, it gets compressed by just atmospheric compression. And so by the time it gets to the LA area, it's warmer than the air at ground level. Now, in LA, you have the added aspect of the Pacific Ocean is cold, so you have cold air here, and then this air comes in and it gets warmed up. And so poor LA and these places in California, they can get really, really terrible air because these conditions can last as long as I have high pressure offshore. Then air is always going to flow from I'm sorry, if I have high pressure inland and low pressure offshore, what's going to happen is it's always going to move from high pressure to low pressure, and you end up, these pressure systems can stay for a while, and so you can have weeks and weeks and weeks in which there's warm air sitting on top of the cold air, and the pollution just in here just builds up to just absolutely lethal levels. This happens in places like Denver, uh, Mexico City. There's a number of places that have it. Basically, mountainous areas are the ones that tend to get these type of subsidence inversions. Fortunately, for us here, the mountains in Korea are not high enough to cause this to happen for the most part, so we don't tend to get this type of substance inversion. But there's another kind we can get. Well, here's Los Angeles. Boy, that air can sure look awful. Uh, and then here's what happens, say, in Mexico City, where you get the cold air. And the other thing too is in mountains too, radiative cooling can compound this because as you have radiative cooling here, as the air gets cold on a slope, it will slide down. And so in the mountain areas, you tend to get radiative cooling causes cold air to come down, and then you get subsidence inversion on top of it. So a place like this happens in Mexico City, and the air can just stay this way for a long time and get really, really bad. It's not that they're polluting more than other places; it's just that they can't dissipate the pollution. And okay, I just another picture. Okay. Oh, I should point out though that another way that these things can form is just from having a high pressure weather system move over an area. So if you look at a map, a weather map, you'll often see H's and L's. So when you have a high pressure system move over an area, basically what that means is that the air is falling into the air. Remember, low pressure is where air is moving upward. So when there's low pressure, you tend to be dissipating the pollutants. But when you have high pressure, that means air is falling into the area. So if high pressure moves over a city, then what that means is air is falling into the area near that city and it's heating up as it comes down. And so these high pressure systems can be very pervasive. They can last for weeks. So I have lived most of my life in Western Washington or Seattle, Washington. We usually have just absolutely enviable air. But every summer or every couple summers, we'll get a situation where you have high pressure over our area for weeks and weeks, and the air just gets worse and worse and worse and worse. And suddenly you can't see Seattle, you can't see the mountains because of all the smog. And it's not that we're making more, it's just that we can't dissipate it. So as long as we have a high pressure system on us, that means the air is still falling into our area. So we're getting subsidence not because of a wind pattern, but just because we have high pressure, which means we have air descending from above. And then there are frontal inversions, which are a little bit less of a concern for two reasons. So basically, if I have a cold air mass moving, in this case, say moving to the right, and there's a warm air mass here, well, warm air has a natural tendency to rise over cold air. So what happens is the cold air is pushing itself under the warm air. And so that's going to make this inversion. Anytime you have warm air above and cold air below, you're going to get an inversion. So there are times when you have a cold front passing through. So for a day or so, you can get really, really toxic air. But the good news is this usually happens. These cold fronts are usually moving. Sometimes they can get stalled, in which case it can last a while. But usually these things are moving. And so you'll get bad air, but it only lasts for a day or two as that cold front passes through. So those are the three different types of thermal inversions and how they're caused and what they do. So see ya.